Lesson 1.3. Geometry is an orderly, systematic body of mathematical knowledge used today to describe the geometric relationships around us. We've started on the foundations or building blocks of geometry, and we began at the bottom of the foundation with undefined terms. Those undefined terms were points, lines, and planes. I've also added space to these terms because the definition of space is based on these undefined terms. Definitions are based on the undefined terms. Postulates. Basic relationships assumed to be true without proof. You may have heard of postulates being called axioms. Theorems. Theorems are statements shown to be true by a logical progression of reasoning. The basic assumptions of geometry, postulates, should be consistent, dependent, independent, and complete. So let's determine if the following set of postulates is consistent. Postulate 1. If two lines intersect, then every other line in the plane intersects one of them. Postulate 2. If two lines intersect, then there is exactly one line parallel to both. Are these postulates consistent? No, they're not. Postulate 1 says that every other line will intersect with one of its lines, while postulate 2 says a line will be parallel to one of its lines. These are contradictory statements. Let's pick an easier one. Determine whether the following set of postulates is independent. Postulate 1. If an animal is named Polly, then it is a parakeet. Postulate 2. If an animal is a parakeet, then it is a bird. Postulate 3. If an animal is named Polly, then it is a bird. Are all three postulates independent? Well, let's go to postulate 1. If an animal is named Polly, then it's a parakeet. Are all animals named Polly parakeets? Not necessarily so. Postulate 2 says parakeets are birds. Is that true? Yes, that is true. Postulate 3 says that if an animal is named Polly, then it's a bird. Is that true? No. An animal named Polly could be a dog. So are these postulates independent of each other? No. Postulate 1 and 2 are true, but postulate 3 requires 1 and 2 to be true. The system of postulates is complete if it forms a sufficient basis for a full description. Postulates will not provide every detail of a system, but every statement expressed within a system will be proved or disproved from the postulates contained. The first postulates in geometry are called incidence postulates. The word incidence means to fall on or lie on. Think about the definition that we already learned about concurrent lines. 2 points lie on line AB. So let's begin with our first postulate from our book. This is postulate 1.3.1. It's called the expansion postulate. And let's take a look at our drawing. It has a plane. It has a line AB on the plane. It has a point C on the plane also, and a point D above the plane. A line contains at least 2 points. A plane contains at least 3 non-collinear points. Space contains at least 4 non-coplanar points. Well, a line contains at least 2 points. If you put 2 points, if you draw 2 points and you draw a line, you will connect those 2 points together. Plane P has at least 3 points. We demonstrated this previously, and it can be named with at least 3 points. They're non-collinear because if they were 3 points that were collinear, instead of being a plane, it would be a line. Space contains at least 4 non-coplanar points. That is a new definition for you. Postulate 1.3.2, the line postulate. Any 2 points in space lie in exactly one line. The drawing shows you that you have point A and point B. A line is drawn through it. That line is also named line K. Postulate 1.3.3, the plane postulate. 3 non-collinear points lie in exactly one plane. So A, B, and C determine the plane P. Why are we learning about these postulates? Well, these postulates are going to be used to explain different shapes that we learn about and theorems that we need to build. Postulate 1.3.4 is the flat plane postulate. If 2 points lie in a plane, then the line containing those 2 points lies in the same plane. So as pictured, you can see the line. It's on plane K, and you can see points A and B. They're also on plane K. Postulate 1.3.5, the line intersection postulate. If 2 lines intersect, then their intersection is exactly 1 point. In the drawing, you see that lines M and N intersect at point G. Postulate 1.3.6, the plane intersection postulate. If 2 planes intersect, then their intersection is exactly one line. And this is difficult to visualize, but think of plane P passing through plane Q. Where they intersect together is line L. Theorems. We use our definitions and our postulates to prove theorems. A theorem is a logical progress of definitions, postulates, and previously proved theorems. So you can actually take a theorem and prove another theorem with it. This is our first theorem. This is theorem 1.3.1. A line and a point not on that line are contained in one and only one plane. This may be confusing. This theorem sounds just like one of the postulates we just learned. Well, it's a little bit different, and we've now proved this theorem using our definitions and postulates. So here's an example of an informal proof in a paragraph form using what we've learned. If you are given a line K and a point C not on the line, the expansion postulate states that the line contains at least 2 points. These points can be called A and B. Because A, B, and C are non-collinear, that means they're not in a straight line. Exactly one plane passes through these 3 points. This is the plane postulate. Since A and B are both in this plane, the flat plane postulate guarantees that line K also lies in this plane. Therefore, exactly one plane passes through a line and a point not on the line. Theorem 1.3.2. two intersecting lines are contained in one and only one plane. You can see line M, you can see line AC. They both lie on the plane and they intersect at point E. Theorem 1.3.3, two parallel lines are contained in one and only one, and this should say plane, not plant. This, once again, is a plane. You still have two lines, but because they're parallel, they do not intersect.